So we have the atomic mass, okay, or the mass number. This is sum of masses of protons and neutrons within a nucleus. So mass number is equal to number of protons plus number of neutrons. And the number of neutrons is symbolized as N, capital letter N. This one may vary for different atoms of an element. So you have one element which has atoms that have different number of neutrons, which make them in the end have different mass numbers. So some elements may have 2 or more atomic masses. We'll see that as we go. So what else do we need to know here? Protons and neutrons contribute to the whole mass of an atom. That's like we said, mass number. That is the mass of protons and neutrons. The atomic mass number or the atomic weight, M, indicates the total number of protons and neutrons in the nucleus. So there are quoted values of atomic mass number, which are based on the atomic mass unit, or the AMU, which is 1/12 the mass of an atom of the isotope of carbon, which has a nucleus with 6 protons and 6 neutrons. So the AMU has a measured mass of 1.6598 times 10 to the power minus 27 kilograms. And quoted values for atomic mass number are not all integers because of what are known as mass defects or the existence of isotopes. What are isotopes? These are various forms of an element that have the same number of protons, but a different number of neutrons. So please keep this in mind to say that the quoted values of atomic mass number are based on the atomic mass unit, which is 1/12 the mass of an atom of the isotope of carbon, which has 6 protons and 6 neutrons. Okay, so we have a table here of subatomic particles. So we have the proton here, the mass in kgs, the neutron mass in kg, as well as the electron here. Then you have your charges here. The neutron is neutrally charged, relative mass 110, and relative charge. You have the charge over there. Atomic weight, repeat here, this is a weighted average of the atomic masses of the atoms naturally occurring isotopes. Then the AMU, this is 1/12 of the mass of the carbon isotope whose nucleus, whose neutrons there is 6 and proton 6. So 1 mole of the substance is equal to 6.023 times 10 to the power 23 atoms or molecules, which is known as Avogadro's constant. So there we have our periodic table, okay, which is an arrangement of our elements, naturally occurring elements. So you have in the periodic table right there, you have your element. With every element, there's the Z's and the A. So you have your atomic weight at the bottom and the atomic number at the top, each and every element. For example, carbon here. The atomic number is 6 and the atomic weight is 12. Oxygen, the atomic number is 8, while the atomic weight is 16, and so on and so forth. So for all the elements listed in the periodic table, you have the atomic weights shown. So there's this also, and this is also a periodic table, just slightly different from the other one. There are some periodic tables that are more detailed, and others are less detailed, depending on what information you want to pick out of there. Okay, so we come to what are mass defects. So a mass defect occurs when measured mass of atom does not equate with the sum of masses of protons, neutrons, and electrons. So according to Einstein's theory of relativity, mass and energy are related. Thus, you have your energy formula there. And where m is mass in kg, c is the velocity of light, and E is the energy in joules. Okay, that's a common formula also. Grab this a different. Energy equivalent of mass defects is per nucleon is the binding energy per nucleon, and the value of mass defect per nucleon varies with the atomic mass number. Okay, and elements with the greatest mass defect values are those with atomic numbers in the range 40 to 100. So the elements that have the greatest mass defect values are between 40 and 100. So the periodic table is very easily able to spot them. So this is the relationship between mass defect and atomic mass number. As you can see on our y-axis, we have the mass defect, nucleon, and the x-axis, we have our atomic weight. So with increasing atomic weight from around here, around 50, going up, you see there's a rise now. So as you are increasing your weight, what happens to the defects? They also begin to increase. While here is a drop for aluminium somewhere there. When elements of high atomic mass number disintegrate into nuclei of lower mass number, okay, so that is the higher mass defect values, mass will be converted into a large energy emission. This is a principle involved in nuclear fusion reactions and harnessed in nuclear reactors for power generation. The nuclear fusion of hydrogen nuclei to form helium will result in a very large emission of energy. Okay, so that is the same principle that is used in what is known as the hydrogen bomb. The release, okay, or the emission of a high amount of energy during a nuclear fusion of hydrogen nuclei from helium. In chemical reactions, as opposed to nuclear reactions, the changes which occur are confined to the outer electron shells. So in chemical reactions, you are more interested in those electrons that are in the outermost shell. You're not interested in the nucleus. Okay. But however, for nuclear reactions, they're interested in what is happening in the nucleus or the nucleus. Energy changes in chemical reactions are of an externally small order in comparison with the energy changes accompanying nuclear reactions. So from that, what do we get? We get to say that nuclear reactions emit more energy, much more energy than chemical reactions do. So we come back to isotopes again. These are atoms of the same elements, like we mentioned earlier, which poses different atomic mass numbers. That is, there is a variation in the number of neutrons in the nucleus or in the nucleus. There's a variation in the number of neutrons. So an example is two isotopes of hydrogen occur in normal hydrogen. So your Z is 1, and your mass and your molecular weight is 1. And the deuterium, which is Z1, and your M is equal to 2. The third hydrogen isotope is known as tritium, which is Z1 and M. Molecular weight increases to 3. This is formed by the bombardment of lithium and boron by neutrons. So the tritium is radioactive. Carbon also has 3 isotopes with the mass numbers 12, 13, and 14. While C14 is radioactive, carbon dating, remember, I hope that rings a bell. So your C14 permits the use of carbon dating techniques for determining the age of ancient remains. So it's in order for us to determine the age of ancient remains, we use C14. So other than naturally occurring isotopes are created, so other than the natural occurring ones, isotopes are created also by means of nuclear reactions. These are radioactive and disintegrate spontaneously with the emission of radiation. Isotons, what are they? These are nuclei of different elements with the same mass number. So an example there you have of argon 40, which has 18 protons and 22 neutrons. Calcium 40 also has 20 protons and 20 neutrons. So these are known as isotones. These are nuclei of different elements with the same atomic mass number. So we look at atomic models here now. So with time, in the latter part of the 19th century, electrons could not be explained in terms of classical mechanics. So for a larger part of the later part of the 19th century, scientists were still trying to figure out, they couldn't really understand electrons. Okay, it was hard for them to explain them in terms of classical mechanics. They knew they were there, but they couldn't really explain their properties. So a set of new principles and laws that govern systems of atomic and subatomic entities were established and came to be known as quantum mechanics. So this is what is known as quantum mechanics. There's also the quantum theory, relative, and all those terminologies that later on they got to be discovered. So, however, quantum mechanics is beyond the scope of our study. However, coming back to what we are entitled, what we're supposed to study, we're first going to look at the Bohr atomic model. The Bohr atomic model is this model here. Okay, so this was by a scientist called Bohr, who helped us to illustrate how electrons, okay, may be arranged in an atom, how the nucleus consisting of the protons and the neutrons, as well as the electrons in the outer shell may be arranged. So according to his theory, he believes that the atom, the electrons are, in shells. They are placed in orbits. They are in shells, in these orbits. That's where they're arranged, and for each particular orbit has a shell has a designated number of electrons that can sit on it. So as electrons are assumed to revolve under this theory, or in this atomic model, electrons are assumed to revolve around atomic nucleus in discrete orbitals. And the position of any particular electron is more or less well defined in terms of orbitals. So for the inner one, as you know, the maximum electrons that it can carry is 2 electrons. The next one, the next shell, the maximum is 8. The outer shell there, the maximum is 18, and so on and so forth. So electrons are permitted to have only specific values of energy. So these are more like energy levels. The electron energy is quantized. So this, the electrons here in this innermost shell have a certain energy level. The ones in this shell also carry a certain energy level, and so does the next one. That is the theory behind this particular model. So what else can we learn from Bohr's atomic model? Electrons are permitted to have only specific values of energy that we looked at already. They're known as energy levels or energy states. Then they may change these levels by absorbing energy, thereby going to a higher level, or emitting energy by going to lower levels. Energy is absorbed or emitted in discrete packets called quanta, where one quantum of energy is equal to hf, where h is the Planck's universal constant, and f is the frequency of radiation. That is the understanding behind. So Bohr model was found to have significant limitations because of its inability to explain several phenomena involving electrons. So the electrons, unfortunately, they don't always follow these energy levels according to this model. And that's the limitation that this particular model has. There are certain behaviors that electrons have that this model fails to explain accordingly. Okay? So that was the limitation that comes with Bohr's model. So like I said, I'll repeat that again. In this model, the energies of the electrons are quantized. That is, the electrons are permitted to have only specific values of energy. An electron may change energy, for example, but in so doing, it must take a quantum jump, either to an allowed higher energy. To an allowed higher energy comes with absorption of energy, or to a lower energy, which comes with emission of energy. Okay, take note of that. So a quantum jump either to an allowed higher energy, when it goes to an allowed higher energy, this comes with absorption of energy. Okay, so energy is taken in, is required for it to go to a higher energy. Then when it's going to a lower energy, what happens? Energy is emitted, or an emission of energy occurs. Then there's also what is known as the wave mechanical model. So to overcome the deficiencies in Bohr's model, the wave mechanical model was established. So under this model, the theory is that the electron is both wave-like and particle-like, and that the electron is no longer a particle in a discrete orbital, and that the electron can be at various locations in a discrete orbital, or they can be uncertainty of its location. That's the theory behind the wave mechanical model. And also the two models, Bohr and wave mechanical, are used in our study. So we're going to apply both. Model usage would depend on which one gives a simpler explanation. We come to electron configuration. So quantum theory requires that 4 quantum numbers be defined to give a complete description of the energy state of an electron. So we have what is known as the first or principal number, okay? Symbolized as n. So n can be 1, can be 2, can be 3, or 4. So with n, the description of general energy level of electron is in terms of distance from the nucleus, that is the shell containing the electron, and is denoted as K1, L2, M3, N4, O5, P6, and Q7. What else do we need to know here? The second quantum number is L. So L can be 0 to n to the power -1. So what is this second quantum number? This is a measure of angular momentum of electron and is denoted by SPDF. So S is equal to 0, P1, D2, and F3. You'll understand me a bit later in our example. Then there's also the third quantum number, okay, M with an index of L. This one describes the magnetic moment of an electron. Then the fourth quantum number, which is M with an index of S. This one can be plus minus a half. So this one so the 4 quantum numbers must be defined to fix the energy levels of an electron. So the shell designation is K, L, M, and N. Principal quantum numbers are 1, 2, 3, and 4. The subshells, we have S, P, D, and F. S, P, D, and F. Then the number of states, we have 1, 2, 3, 4, 5, 6, and 7. Okay, so a continuation there on electron configuration. The values of energy that are permitted for electrons, called electron states, can be filled using the Pauli exclusion principle. So what does this principle state? This principle states that each electron state can hold no more than 2 electrons which have opposite spins. Therefore, SPD and F subshells can accommodate 2, 6, 10, and 14 electrons respectively. However, not all possible states in an atom are filled with electrons. Electron configuration or structure of an atom will therefore represent how the states are occupied. The number of available electron states in some of the electron shells and subshells. So that is, you have your principal, for example, can be 1. Shell designation will be K. The subshells will be S. Number of states will be 1. And the number of maximum electrons per subshell will be 2. That is an example. And we'll see more as we go. So there's this example here. So there's 1s1. This is for hydrogen. So 1 is representing the shell or the first quantum number. 1 here is representing the number of electrons. S here is the subshell or the second quantum number. So it's S, then P, then D, then F. We'll follow the sequence as we go. So the hydrogen is the simplest. So you have your 1. So a hydrogen here, the symbol here in quantum, the quantum number for hydrogen is 1, S1. So 1 here is representing the number of electrons. Hydrogen has 1 electron. Then in this table here, we have helium. How many electrons does helium have there in its outer shell? It's 2. So helium will be 1s2. Okay. Then sodium has an atomic number, has 11 as its atomic number. So meaning the number of electrons should give us 11. So this is the formula, the atomic number for sodium. This is how it's written. So it's 1s2. It's filled. There you move to the next. Shell, which is S, 2s. So with 2s here, the maximum number of electrons it's taking is also 2. Okay, so we have 2 here and 2, 4. So 11 minus 4, we have about 7 more electrons that need filling. So we come to this next shell here, which is 2p. So 2p takes a maximum number of 6 electrons. So we'll fill it up, which is 2p6. Then this gives us 10, isn't it? Meaning there's an excess 1. We move to the next shell, which is 3s. 3s takes up a maximum of 2. So we have 1 left, and we simply just write our 1 here. So when you add these indexes, the top indexes here, the numbers, they'll give us 11, okay, which is equal to the atomic number for sodium. This is one example here. We'll look at others. So for the purpose of our discussion, we'll concentrate on the outermost shell. The electrons in the outermost shell are commonly known as valence electrons. Valence electrons. For example, copper is, copper, we know it's copper +2. The +2 is depicting the number of electrons that are in its outermost shell. That's one example. Electrons are important as they participate in bonding between atoms to form atomic and molecular aggregates. So the valence electrons also determine the physical and chemical properties of solids by virtue of their bonding. So valence electrons are very important because other than just participating in the bonding that happens between atoms to form atomic or molecular aggregates, they also determine the physical and chemical properties of solids by virtue of their bonding. And when all the outermost shells are filled with electrons, they are said to have a stable configuration. An example of elements that have stable configurations are the inert elements from our periodic table. For example, argon. Argon is said to have a stable configuration because its outermost shell is filled with electrons. There's no more space for anything, therefore it's more stable, and it's also chemically stable as a result. Rarely it goes into reaction with other elements. So in a stable electric configuration, the outermost shell is completely filled with electrons. For example, here we have neon, argon. As you can see there, the first shell takes a maximum of 2 electrons. The second shell, which is 2s, takes a total amount of 2 electrons. And the third shell here, 2p, takes a total amount or a maximum amount of 6. And for neon here, it only has 10. So they fill up everything completely without leaving any space. Argon, the same thing here happens. As well as our third element, the same thing happens. So we have, this one is more detailed actually, we can go for. So after this shell, 2s, 2p, the next one is 3s, okay, the maximum is 2. After 3s, the next shell is 3p, which takes up a maximum of 6. After 3p, the next shell is 3d, which takes up a total amount of 10. After this one is 4s. After 3d shell is the 4s shell, which takes a total amount of 2. After 4s, you have 4p, which takes a total amount of 6 electrons. So looking at the atomic number for krypton, you find that all the shells here have been filled. So these are known as inert gases. For inertness, reason for inertness is no incompletely filled outermost shell. Okay, this is what we've already looked at. No incompletely filled outermost shell. So concerning the periodic table, all elements in the periodic table can be classified according to electron configuration. And most of the elements come under metal classification. So most of the metals that we have, most of the elements that we have in the periodic table are actually metals. And these elements are sometimes called electropositive elements. And this indicates that they are capable of giving up their few valence electrons to become positively charged. So if, for example, copper, I'll come to copper because that's one of the common metals we have in our country. So if the copper has a +2, meaning signifying that its outermost shell has 2 electrons there. So for it to become positive, what happens when there are more? When it gives up those 2 electrons, it becomes more positively charged. Okay, because you still have your protons remaining in the nucleus, which have not moved. So it becomes more. The more electrons, as it loses electrons, it becomes more positively charged. When it loses even just 1 electron, it becomes more positively charged. The elements situated on the right-hand side of the table are electronegative. For example, fluorine, chlorine, those are electronegative elements. They are situated on the right-hand side of the periodic table. What does this mean? It means that they readily accept electrons to form negatively charged ions. They readily accept electrons to form negatively charged ions. Or sometimes they share electrons with other atoms. So before we get there, you can simply have a look at the recommended literature. In Callister there, under the topic atomic structure, you find various quantum numbers for different elements. For example, carbon would be 1s with an index of 2, 2s with an index of 2, 2p with an index of 1. So meaning for the third shell which is 2p, sorry, which is an index of 2, with the third shell which is 2p, only 2 electrons fill that one up. That's for carbon. So carbon has an atomic number of 6. So 1s2, 2s2, and 2p2. That is 2, 4, 6, 6, which balances. So just quickly, you can just go through them in your own time, one by one, just to see the sequence and how it is done. So bonding forces and energies. We come now to bonding forces and energies. So for that bond to form, there should be a force, isn't it? That is supposed to attract, so an attractive energy. A force or energy that should make this bond possible. That should make one atom want to be attracted to the next atom. So in order for us to understand the many physical properties of materials, a knowledge of interatomic forces that bind atoms together is very crucial. So as an example here, we consider two atoms brought together in close proximity from infinite separation, and we'll look at the forces that come into play. So we have two atoms brought together, very close together, okay? Like just literally next to each other, you place two atoms there. And we're going to study what forces come into play, okay, when you have these two atoms in close proximity from infinite separation. So this is an example of what you expect to see. So you have on the left, on the y-axis here, you have attraction increasing as you go up this way. The more you go, as you go higher, the more positive. And repulsion here, the more, the further you go down, the more negative. So understanding of materials enhanced by a knowledge of the interatomic forces that bind atoms together. So at small separation distances, where the separation distances are small, each atom exerts forces on the other. And the forces are of two types. There's the Fa, this one here, which is known as the attractive force, and there's the Fr, which is known as the repulsive force. And R here in this case is the interatomic distance, which is the distance between the two atoms there. So the origin of Fa, which is the attractive force, it depends on the particular type of bonding that exists between the two atoms. And then also the Fr, which is our repulsive form here. This force arises from interactions between the negatively charged electron bonds or the negatively charged electron clouds for the two atoms. And this one is very important, only at small values of R, okay, only at small values of our interatomic distance. Because the outer, what happens is that as your R is growing, the outer electron shells of the two atoms begin to overlap. Okay, they begin to overlap. Okay, so like I said, bringing two atoms together, two forces will arise. The force of attraction, which is our Fa, from here, I'll come back to this one here, and the force of repulsion. The two forces are a function of the separation or the interatomic distance. So the force of attraction Fa depends on the particular type of bonding that exists between the two atoms. When two atoms are close by and their outer electrons overlap, a strong repulsive force Fr comes into play. And the net force is the sum of the two forces. So the formula there, net force is equal to Fr plus Fa. The dependence of repulsive, attractive, and net potential energy on interatomic separation for the two isolated atoms is given by this particular formula, okay, which is simply just the net force. Just wait to get the next slide. Okay, so when FR and FA are balanced, then they equal as 0. So where your repulsion force is equal to your attractive. So if you have a negative value there, -10, for example, and then the FA is a +10, your answer will be 0. So there is no net force in such a case. And the absence of a net force implies that the arrangement is in equilibrium. At equilibrium point, what happens? The centers of the two atoms remain separated by the equilibrium spacing, which is known as R0. And for many atoms, R0 is approximately 0.3 microns. The mathematical relationship between energy E and force F is given by that formula there below, which is a function. So I'll come back to our graphs. Whatever reason, my laptop is taking long to get back to the graph. But anyway, I'll move forward. You can still do that by yourselves. Okay, so there is our function there. Then for atomic systems, you have the En, Ea, Er, which are the net, attractive, and repulsive energies for two isolated and adjacent atoms. So we'll be solving for that. So from our earlier graph, unfortunately, I'm not able to access it. The bonding energy for the two atoms, which is E0, it represents the energy that would be required to separate two atoms to an infinite separation. That's the energy that is required to separate two atoms to an infinite separation. Materials having large bonding energy typically have high melting temperatures. Okay, so materials that have high bonding energy typically have high melting temperatures, while those with lower bonding energy are in gaseous states and intermediate bonding energies in liquids. So basically, I think the logic behind is that if it takes in so much energy to make a bond, then it should require just as much energy to separate it. That's the logic behind this. And therefore, a number of material properties depend on bonding energy and bonding type. So where if there's a bond that is taking up so much energy, it means that bond is strong enough, isn't it? It's able to withstand temperatures and only melts. The bond only breaks after you heat it for so long. When you increase the temperature, that's why we have them typically having high melting temperatures. And those bonds that are easy to form, they're also easy to break, in short. So therefore, a number of material properties depend on the bonding energy and the bonding type. Okay, I'll just let you read through that again before I move to the next slide. Okay, so we come to nucleus and radioactivity. Presence of neutrons plays a major role in ensuring stability of atom nucleus. But the nature of the nuclear binding or the bonding there is not fully understood. And what else do we know? Elements with atomic numbers greater than 83 do not possess a stable nuclei. And these are just notes for you points for you to take note. The large nuclei disintegrate spontaneously, emitting energy and particles, what is known as radioactivity. And the three types of particle emissions exist, which is namely alpha, which is equal to helium nucleus, the beta particles equal to an electron, and the gamma radiation, which is high frequency radiation. The rate of radioactive decay is proportional to activity at that instant. So this is not anything strange to you. I know you covered this in probably physics or science. This material that you already know, but anyway, nevertheless, we'll still go through just in case, just a reminder in case you have forgotten. So if L is activity at some time, then we have this formula here, where gamma is a radioactive constant. However, when the above equation is integrated, it gives us this new formula where I with an index of 0 is the initial activity at 0 time. The initial activity at 0 time. So an important characteristic of any radioactive substance is its half-life, which is symbolized as T, or the time required for half of radioactive nuclei to disintegrate. So this is the time required for half of the radioactive nuclei to disintegrate. That is, you have our formulas here. These are also no strange, these formulas are not strange to you. You know them already. There's an example here concerning half-life. So a radioactive cobalt-60 has a half-life of 5.3 years. What is the radioactive constant for cobalt-60, and how long would it take for the activity of a sample of cobalt-60 to reduce to 85% of its original value? Okay, so based on the formulas that we just looked at, you have the following working. And your answer there in the end is 1.24 years. We are going to have a similar question as part of the assignment. So there are three types of primary or chemical bonding. However, when it comes to half-life, we will not really cover it. It's quite large, especially if you've forgotten most of the material on carbon dating and how to find the half-life. I urge you to go through your material, go through Callister, for you to have a better understanding. For now, we have to unfortunately cruise through because the curriculum is quite vast. So we continue with bonding forces and energies. There are three types of primary or chemical bonding. So there's namely ionic bonding, covalent, and metallic. We look at each one of them and look at their characteristics. So these are primary or chemical bonds. These are ionic, covalent, and metallic. For each type of bonding, valence electrons are involved. Remember, valence electrons, that's the number of the electrons that are in the outermost shell of an element, of an atom. So generally, each of these three bondings arise because atoms want to assume a stable electron configuration. An example of ionic bonding. This one takes place in compounds which have metallic and non-metallic elements. So it's always found in compounds that are composed of both metallic and non-metallic elements. And these are elements that are situated at the horizontal extremities of the periodic table. So from one extreme end to the other extreme end of the periodic table. So you have, for example, sodium, the far left, and chlorine on the far right. That's a typical ionic bond that forms there, where sodium and chlorine have this transfer of electrons. So transfer of electrons happens. You see, chlorine has 7 electrons in its outermost shell. Okay, it just needs 1 to make it complete. Sodium, however, has in the outermost shell, it has 1 electron. So if it lost that electron, it would be stable. And if it gave that electron to chlorine, that needs that 1 electron to become stable, then they'll both end up being stable. So the transfer of electrons, that happens. So this is an example of the Coulombic bonding forces that happen in ionic bonding. So there's these forces which are equal. One that's drawing the chlorine to the sodium, and the sodium to the chlorine. These are equal forces, also known as Coulombic bonding forces. It's typically how atoms are arranged in ionic bonding. So both metallic and non-metallic elements have a net electrical charge, since electrons and protons in each atom no longer match. So metallic elements become positively charged ions, while non-metallic become negatively charged. The bonding arising from this arrangement of two different elements is known as ionic bonding. So meaning the elements, just before we come back to this point, in case there's some that may have not understood, the elements that loses an electron, in the case of sodium and chlorine, which one loses an electron? It's the sodium. So as it loses an electron, it becomes positively charged. Okay, and then the atom that gains an extra electron, an electron is negatively charged. So if it adds more negativity to itself, it becomes negatively charged. But the last point here, the more valence electrons the metal transfers, the stronger the bond, and can be evidenced in the melting point. So if you have a metal that is giving up 3 electrons to form a bond, that bond will be much stronger than a bond that is, for example, the example that we just looked at, sodium and chlorine. Example of sodium that just had to give up 1 electron in order to form that bond with chlorine. It won't be as strong as a bond where an element, a metal, for example, aluminium, gives up 3 electrons in its outermost shell. And that is also evidenced in the high melting mechanism. So what else can we say here? Melting point of sodium chloride, where 1 electron is involved, is 801 degrees Celsius. Magnesium oxide, where 2 electrons are involved, is 2640 degrees Celsius. And zirconium carbide, where 4 electrons are involved, has a melting point as high as 3500 degrees Celsius. That is very hot. Much, much hotter. Probably than your oven. It's much, probably almost 10 times hotter. So ionic compounds are characteristically hard and brittle. That's worth noting also. They are characteristically hard, not all of them, but they are characteristically hard and brittle. So also an ionic bonding here, being of opposite charge, they will be strongly attracted to one another by an attractive force, which is Fa, with this formula here. Remember, we looked at the forces and the energy, the bonding forces and the energies earlier. Okay, so ionic bonding, these are said to be non-directional, implying that the magnitude of the bonds is equal in all directions around an ion. There's no particular direction, in short, but the bonds, the magnitude of the bonds are equal in all directions around the ion. Bonding energies in ionic compounds are relatively high and are a cause of their high melting temperatures. So if the energy needed to form the bond is high, like I said earlier, the principle you need to follow, then even the energy that is required to break that bond will also have to be even much higher. So we come to covalent bonding. What is covalent bonding? This is also something that you know and have heard before. So these are a stable electron configurations that are assumed by the sharing of electrons between adjacent atoms, like in the example you can see there. So two atoms will each contribute at least one atom to the bond, and the shared electrons may be considered to belong to both atoms, like this case here. So this is CH4 methane. You have your carbon here, and you have your hydrogen in the side. Okay, or much better even on the diagram on the right. So what do we know about carbon? How many electrons does it have in its outermost shell? It has 4 valence electrons. All hydrogen has 1 valence electron. So what happens? Carbon is sharing its electron with hydrogen. On this side, on essentially both sides. So what happens in the end? Carbon also becomes stable because it has acquired 4 electrons on its shell, making it 8, making it complete and stable. While the hydrogen also is acquiring 2, okay, its outermost shell, making it stable also. So they both benefit in this bond, and in the end you have your CH4 methane formula. So what do we know about covalent bonds? They are directional. This means that between specific atoms, so meaning it is between specific atoms, and it may exist only in the direction between one atom and another that participates in the electron sharing. Only in the direction of participation are they directional. So an atom can bond with 8 other atoms. For example, here chlorine has an N of 7, isn't it? Number of atoms in its outermost shell is 7. So meaning it can bond with 1 more. Okay. Then there are also non-metallic elements, for example, this same chlorine, that form molecules, as well as molecules containing dissimilar atoms, such as methane, the CH4 we looked at earlier, or H2O water, HF also. These ones are covalently bonded. So aside from just bonding happening between elements, atoms from different elements, sometimes the bonding, covalent bonding can be formed between atoms of the same elements. For example, here, as you can see, we have the chlorine atom forming here. So there's a sharing of atoms, and eventually your chlorine molecule is formed. So carbon can bond with 4 hydrogen atoms. So carbon can bond with 4 hydrogen atoms. So that's the maximum for the outermost shell is 8, isn't it? So 8 minus 4 gives you 4. Here, what is the shell here? The maximum is 8, isn't it? 8 minus 7, which is 1. So it can share. It can share an electron there to make it stable, or to form a molecule in this case. So what else do we know? Covalent bonds are strong. An example is diamond with a melting point of 3,550 degrees Celsius. So they can either be strong or they can also be weak. An example is bismuth, melting point, which is 270 degrees Celsius, very low compared to the 3,550. Then what else do we know? Polymers, also plastics, are known as polymers. They are covalent bonds. However, a bond can be partially ionic and partially covalent. This is very possible. Okay. So if the separation in the periodic table is wider, for example, on one end you pick chlorine, on the other end you pick sodium, that bond will most likely be ionic. However, If the elements are closer together in the periodic table, this is most likely going to be a covalent bond. You can take note of that for you to distinguish. This will help you distinguish or identify which elements are ionic and which ones are covalent. There's also a formula that we'll look at further. So continuation with covalent bonding. This can be described as directional. We said that already. The bond is between specific atoms and may exist only in the direction between one atom and another that participates in the electron sharing. We have chlorine there, tellurium, as well as antimony here, SB. Okay. This is a spiral chain. These are like more or less like corrugated sheets. We have our chlorine atoms here. So these are just a different type of bonds. So you can see one is forming the spiral one, these ones are corrugated. So in continuation, this is a formula that we use to determine what kind of bonds the two elements have. So it's also known as the percentage ionic character of a bond between elements A and B. Between elements A and B. So you have our formula there where XA and XB are the electronegativity values for the respective elements and can be found from the following figure. So even just on the periodic table, there are certain periodic tables that will actually in there give you the electronegativity values for each and every element. An example is this type of periodic table. As you can see here, for example, you have boron here, it's 2.0 as its electronegativity. Hydrogen, that's the value there. Molybdenum also has the value there. Nickel, 1.8. As you can see, copper is 1.9. So you can easily just quickly pick your values from there and feed them into your formula here. This is exponential. So 1 minus exponential, you have negative 0.25 close bracket. So you have XA plus XB. Okay. Oh, one more thing to note here, A is the most electronegative. Okay, so you have two elements there. So the most electronegative is the one that you put as your XA here. So the vast field of industrial polymers is also predominantly concerned with covalent bonds. We'll look at polymers as a whole topic together separately as we go. We'll come to metallic bonding. What is metallic bonding? So metals typically have 1, 2, or 3 valence electrons. This is the number of electrons in the outermost shell. Valence electrons are not bound to an atom, but are free to drift through the entire metal, forming an electron cloud. That's the difference between metals and other materials. They form, the electrons are free to roam around, okay, and forming what is known as an electron cloud. The remaining non-valence electrons and the atomic nuclei form the ionic core, so more electropositive. Or the electron cloud is negative. Free valence electrons shield the positive ion core. Okay, so these free valence electrons will be shielding the positive ion core. What else do we know about metallic bonds? That they are non-directional, and the free valence electrons hold the ion core together. And also, as we know, metallic bonds are good conductors. And metals are also good conductors. So this is what happens here. Let's look at the bonding forces and the energies, the bonding forces and energies. So you have your ion cores there and your free valence electrons protecting, more like protecting the ion cores, huh? Protecting the ion cores. This is the C of valence electrons. They're just free roaming free roaming around. Bonds are also non-directional because of the electrostatic attraction between ions and electrons. The bonds also explain the high thermal and electrical conductivity of metals. It's from the bonds that we understand the high thermal and electrical conductivity of metals. So an exam question, it comes as follows. Why are metals good conductors of electricity? Answer is because the electrons are free, the free valence electrons are free, thus allowing electricity to pass through them. Since the valence electrons are not bound to any particular atom, they can move through the lattice under the application of an electric potential, causing the current flow, and can also, by a series of collisions with neighboring electrons, transmit thermal energy rapidly through the lattice. To understand more into detail what a lattice is, basically just a unit of the atom structure. Metallic objects are opaque due to their bonding. Did you notice how metallic objects are opaque? I don't think there's a metallic object that is transparent, through which you can see, or that allows light through it. If a ray of light falls on a metal, the electrons, being free, can absorb the energy of the light beam, thus preventing it from passing through the crystal and rendering the metal opaque. Okay, this is quite interesting. And the electrons which absorb the energy are excited to high energy levels and subsequently fall back to their original values with the emission of light energy. In principle, the light is reflected back from the surface of the metal, thus the high reflectivity of metals. No wonder we say metals are shiny and whatnot, because of these principles that we've just taken note of here. So there's also what is known as the van der Waals bonds. Van der Waals, named obviously after the person that discovered them, the scientist that discovered them. So the three strong primary types of atomic bonds are ionic, covalent, and metallic, all occur because of the need for atoms to achieve a stable electron configuration. So there's a need for atoms to be stable. That's why they're either giving out electrons to be stable or accepting electrons to be stable, depending on what is on their outermost shells, what their valence is. However, when a stable electron configuration exists, some form of bonding force between the molecules must be present. Since these elements will all liquefy and ultimately solidify at low temperatures. Okay, so some form of bonding force between the molecules must be present. And the van der Waals forces are universal to all atoms and molecules, but are normally so weak that their effect is overwhelmed when primary bonds are present. An example is polymers. Polymers are typically covalent bonds. However, they also have some forms of van der Waals also stemming out from some of the atoms. So for a hydrogen bond, highly polar molecules form when hydrogen covalently bonds to a non-metallic element. So you have therefore the high polar molecules form when hydrogen covalently bonds to a non-metallic element. For example, here we have oxygen. This is an oxygen atom here, and we have our hydrogen and hydrogen, so it's basically water. So you have a dipole here forming, isn't it? More negative on this side and more positive on this side. What you have forming, or dipoles, dipole. Let's prefer the word dipole. So hydrogen bonds are an example. The strongest and most important example of a dipole interaction occurs in compounds between hydrogen and nitrogen, oxygen, or fluorine. One example that we just looked at was that of hydrogen and oxygen. Okay, so this is an assignment that I want you to do. So it carries how many questions? 1, 2, and 3. So we end here. We've looked at the different types of bonding forces, the different types of, we've looked at the different types of bonds. Okay, we also looked at bonding forces and energies, and generally the atomic structure. So we've basically covered that material. And our assignment, our first assignment is here. Write down the values of M, atomic mass or atomic weight, and atomic number 4. The element X formed from thorium and 6 alpha and 4 beta emissions. The element Y formed from uranium and 6 alpha and 2 beta emissions. Okay. And the question 2 also here, which has to do with radioactivity. And question 3 here, which has to do with electron configuration. Elements X, Y, and Z have atoms with outer electron shell configurations containing 4, 7, and 8 electrons respectively. State and describe the type of bonding which is likely to occur in the following cases: between atoms of X, between atoms of Y, and between atoms of Z. Between 1 atom of X and 4 atoms of Y. Due date is 31st August 2021. So please, I urge you to look into this assignment. Look into this assignment and answer the questions accordingly. Okay, so if there are any questions, we can still have another lecture. In our next lecture, we'll cover just questions that you may have from this lecture as we continue to look at our next topic. Thank you.